are in listen-only mode.
Welcome to another WCAI webinar entitled Smart Energy Solutions Using Fuel Cells. I am Chris Horne of LBA Group and the moderator for today's exciting presentation. Today's webinar on smart energy and fuel cells will last for approximately 40 minutes with a 15 to 20 minute question and answer session at the end. You may submit questions electronically using the question box, and I will forward those to the speaker. The last decade has seen tremendous growth in wireless communications. This growth has sharpened operators' focus on deployments, cost, and how to power their infrastructure. There are currently more than 1,300 hydrogen fuel cell systems serving as backup power for telecommunication sites in North America. These fuel cells can also be used as part of a telecom operator's managed power strategy, positively impacting its bottom line. When the operator can remotely start hundreds of systems to reduce peak energy demand, they can positively impact their utility rates and receive credits from the electric utility or government agencies. In the end, the fuel cell becomes a viable tool in telecommunications operators' overall energy management model while continuing to provide robust, long runtime, clean backup power. This webinar will offer some examples for optimizing your energy usage. Our speaker today is Joe Blanchard of ReliOn. ReliOn is a world leader in the delivery of hydrogen fuel cell systems for backup power at communication sites, with more than 4.1 megawatts of fuel cell product delivered to 1,400 customer locations. ReliOn works with wireless, wireline, and government communications customers to provide solutions to power requirements between 50 watts and 20 kilowatts. Joe has served as ReliOn's Chief Operating Officer since May of 2011, having held the position of Vice President of Product Line Management since 2005. Blanchard spent the previous 18 years with Fujitsu in Richardson, Texas. During his tenure at Fujitsu, he held various management positions in development, product management, product support, and services. Prior to Fujitsu, he worked in product development for Rockwell Westcom and for GTE Automatic Electric. For more than 27 years, Blanchard has been involved in the design, development, marketing, and support of products spanning DLC, DSLAMs, fiber to the home, fiber to the curb systems, telecom cabinets, power systems, optical transport, DWDM systems, Class 5 switching, and PBX systems. Without further ado, I'd like to introduce Mr. Joe Blanchard.
Thank you, Chris, and good afternoon, ladies and gentlemen. It's a pleasure to be here with you today, and as Chris said, that if you have questions, you can enter them, and we'll get to them at the end of the presentation. So with that, I'm going to go ahead and get started. So today we're going to talk about a variety of topics, but the solution that we're looking at is using the fuel cell to support energy management as well as backup power or power solutions around the telecommunications environment. So today I'll give you a brief introduction of who ReliOn is and then talk a little bit about fuel cell technology and the architecture of fuel cells, and then how a power system would work at a site, how it's hooked into the site, and then some details about what enables the fuel cell to be used as an energy management tool, and then get into kind of the meat of the presentation about incentive programs and programs centered around energy management. And we'll talk through those and then go through a hypothetical model that gives you examples of how you could use the power systems to support utility programs and how those will be a benefit both from a reliability standpoint as well as a monetary value standpoint. And talk a little bit about sustainability at the end, and then wrap it up and go to questions. So just a brief introduction of ReliOn. Our team is approximately 50 staff located in Spokane, Washington, and we're a technology company that has been specifically formulated with staffing around communication systems. We have a core of fuel cell engineers and developers and R&D scientists, but mainly on the commercial side and the customer-facing side. Most of us come out of the communications environment. It's our target market and across a variety of sectors, and therefore we've staffed and built the company around that knowledge base and the customer's requirements. The technology that we work in is electrochemistry. Specifically, it's proton exchange membrane fuel cells, and pride ourselves in, even for a small company, maintaining an R&D program down at the material science level, clear up to product engineering and system solutions and turnkey solutions at the customer site. So the products that we've developed range in power levels from about 175 watts up to 2.5 kilowatt building blocks, and those can be added as modules in parallel configurations ranging up as high as 30 kilowatts if necessary for a target application. So the markets, obviously the wireless communications is a big component of our market. We deal with emergency responders, both private and public communication systems, and transmission systems for high-end communications, as well as utility sector for things like SCADA networks, and also transportation networks, again for communication, but also for control and signaling applications within the transportation markets. So this diagram gives a basic view of a cross-section of a cell of a PEM fuel cell, proton exchange membrane. And starting from left, the way that the system works is hydrogen is introduced into the system and reaches a catalyst on the electrode on the anode side of the cell, breaking the hydrogen molecules apart. And what happens is the proton is allowed to electrochemically transfer through the membrane, which is actually similar to a saran wrap plastic, and it builds up a charge on the anode side, which allows them to drive a circuit coming back to the cathode side, where we're introducing oxygen to a similar catalyst arrangement where the oxygen molecule and hydrogen come back together to form water. So the process is is actually quite simple when you look at it in terms of a diagram like this. The electrochemistry is a little more complicated than how I just described, but it's a very basic and simple cell technology, and what we get out of it is for the hydrogen and oxygen coming in, we get the electricity on the circuit, and about 50% of the energy created actually comes off as heat, because in the end it's the heat of formation of water, which we're dealing with at a molecular level. And so the output of the system is electricity, heat, and water, and therefore being very clean and benign to the environment. A site power system, or how the fuel cell would actually apply to a site that we're dealing with in a communication systems. In this case, we just have a generic equipment load shown at the bottom of the diagram. The fuel cell is a simple DC connection. It's a regular DC power output, connects in parallel to the batteries and the rectifier. So it looks, for all intents and purposes, just like another piece of DC equipment, say on the bus. The fuel cell is dimensioned around power. So if someone has a 500-watt load, you just dimension the fuel cell around 500 watts, and then the energy, or the kilowatt hours, actually are derived from the hydrogen storage. So it's a power and energy model that you have to look at to know what you need, and which is different from batteries, because batteries have to be dimensioned for the total energy you want to have stored or consumed at any given time. The system can simply be indoor or outdoor mounted. It can be inside of a environmentally protected cabinet to range full temperature environment that we have anywhere in the world virtually. And very different from internal combustion generators, the fuel cell follows the load, so it only will produce power when necessary. Therefore, it only consumes hydrogen when it's necessary, and only consumes at the rate that it needs to produce power. And so therefore, it maintains a very high efficiency throughout its full operation and can range from output of its 0% of its rated load to 100% of its rated load. So it makes it a very simple solution working on the DC side. The other thing is we look at site solutions that are important is that equipment these days that we're powering the actual load are becoming more efficient. There's a lot of work being done through organizations and by customers to drive higher efficiency in radio equipment and transmitters and amplifiers, and so that's a driver to reduce power, which is a good thing, as well as the AC to DC, the rectifier manufacturers, and anyone else involved in power electronics are working very hard to improve their efficiencies to, again, reduce the power consumption, reduce the costs at a site. And the final thing that's contributing to all this that actually helps in how to manage a site is products on the radio side and the core networks are becoming a little more robust, so the cooling solutions can be eased a little bit. There may not be active air conditioning necessary at every site, where maybe just a heat exchanger or even free air cooling might come into play, which would ultimately improve the efficiency of the site by significant percentage points just by the cooling side of it. So this graphic is kind of an eye chart, but it provides a view of a very extensive but hypothetical network with kind of the optical legacy wireline equipment towards the bottom and the wireless communication systems towards the top of it, showing various locations, both customer premise, office buildings, rooftops, outdoors, as well as even portable systems in cell-on-wheel type applications, or even alternate energy sites that might be off-grid using wind and solar along with fuel cells, where the fuel cell can provide a solution throughout virtually any point on the network, so long as the power and energy requirements match up. You can see that it's not shown at the large central office or the head end where power requirements might be in the hundreds of kilowatts or megawatts of requirements. Not necessarily a good application for a PEM fuel cell, although there's other manufacturers in the fuel cell technology that do make solutions for those larger power sites. There we go. So to make the system work, it requires a remote operation. So embedded within the fuel cell technology is communications interfaces to the network, allowing the systems to be remotely managed and communicated with via an IP network, either from a customer NOC or a remote technician for a third party, which could be, in this case, maybe a utility that has reached an agreement with the communications service provider to manage their systems based on certain utility programs or energy demands on this grid scale. It also could be a third-party operation. There's companies that do aggregation for energy management programs that may step in and then provide management and maintenance of systems and assets, whether that be, in this case, fuel cells. In some cases, it might be air conditioning systems or large industrial power devices that they may manage in this. So the system has to work seamlessly in that network to be able to turn on and turn off at basically a moment's notice to be able to support the programs the utility would have, and therefore really become what we consider a dispatchable asset when you can manage it again, interactively to match up to the demand requirements or the utility requirements on the grid. So back to the diagram of the site power solution. Typically the way that works, the grid is the primary source, and the point here is to show that what we're going to do in managing the fuel cell for the energy programs is not reduce the reliability of a site. So the grid is our primary source, excuse me, and then the fuel cell is managed for the energy program, keeping in mind that it's always available in case there was actually a grid fault. The system would still come on and supply backup power, but in this case we're going to manage it for the energy program. It is designed then to take load away from the rectifier system, and ultimately then it's producing power to the load, taking it away from the energy or the power energy supplied from the grid. So in effect, what the system is doing is arbitrating the amount of power flowing from the grid and the fuel cell. Again, all the while the battery is still available and online. So if any fault were to occur, the battery is still there as another backup. And most importantly, we're not actually switching anything completely off of any power system. So the load is not at risk during any of these energy events. It still has full grid support, full battery support, and full fuel cell support in case if there's any fault or any failure in any one of those sources of power. So let's talk a little bit about the incentive programs that are available. There's a myriad of incentive programs. This is focused on domestic U.S. Programs. There are some international programs available, but I'm going to focus mainly on the domestic scene right now. There's a significant amount of resources available at the Department of Energy website. The link is shown there on the upper right with the diagram. There's a specific area that they've produced with information about how to site, zone, and all the safety requirements and detail requirements around using fuel cells at telecom sites. And it's a fairly extensive list of information there. The left-hand side is a database that is available for state and federal incentives, and the tables below kind of summarize what's out there. So if you just look at renewable energy, there's huge amounts of tax abatements and rebates and different programs that are available if someone wants to take advantage of those to deploy not only fuel cells but other alternate energy solutions. Specifically, the federal government has got an investment tax credit that is available today and through 2016 that equates to $3,000 a kilowatt, or 30% of the installed cost or the basis of the product, whichever one is less. So the example here shows a 4-kilowatt site that is provided at a capital cost of around $26,000, then with full installation, transportation, everything's necessary, about a $50,000 total investment. And then the calculation showing that there's available $12,000 of investment tax credits that can be received back using the IRS Form 3468 that's shown here. And it's a very strong program. It's not as widely used, actually, as the Department of Energy would like to see it used. It's used a little more heavily. This investment tax credit does work for other alternate energies, but it is available and quite simple to go through the calculations. Additionally, at the state levels, the highlighted states have got some very specific incentive programs around taxes, sales tax, other taxes, other rebates that are available. These are very specific to fuel cell applications. If you look across the states, there's a tremendous other amount of incentives and programs available. These are very specific to fuel cells. So some states are much more aggressive about deploying various forms of alternate energy than others are. California being a very strong player in incentives and therefore in the communication sector, particularly in the the traditional cellular wireless carriers. California probably has a majority across the nation of fuel cell deployments today, but it's growing very heavily in the Northeast and the Southeast right now. So I'm moving to the program ideas at this point and talk through a few different programs that are available. And first and foremost, the idea is that the fuel cell is deployed as a backup power solution that's there to extend the reliability in case of long-term outages. And by long-term, I could mean anything from, in wireless sites, anywhere from 4 to 8 to 12, in some cases. In programs we're rolling out right now, we're doing 48 and 72 hours worth of backup are provided at the site. So in that case, it's not a matter of a fuel cell versus a battery, it's a fuel cell versus an internal combustion generator is the model that's typically being used because we're talking about extended run times. So in this case, you've got a variable usage on the load. It comes and goes with traffic, with time of day, with whatever. When an event happens that the grid fails, the fuel cell is going to come on and provide full power to the load for the duration of the outage, and then the utility grid would come back on and take back over. So the cost of operation of this is the same as it is in any model. The fuel cell operational cost will be the same. But primarily this provides the continuity of services and the ability for the operator to maintain their service level agreements, maintain their operating revenues, keep their customer satisfaction high, and so on and so forth. So it provides really a cost avoidance or a interruption avoidance, therefore insurance for the network. Demand response is a fairly common term being used now, at least in the utility world, in the smart grid world, to talk about how something can respond to a demand on the grid and either reduce the capacity or the consumption or affect the load side of the grid to prevent either maybe the requirement to do blackouts or a brownout or some peak issue that the utility is trying to prevent, bringing a new generation solution online in a short period of time, or doing power purchase agreements with another utility where they're going to move capacity from one location to the other. Anytime peaks come into play and shortages are on the grid, the costs go significantly higher both for the utility and the consumer. So this idea is when an event comes and the program typically is the consumer or the company bids into the utility a certain amount of asset or generating capacity or load to be able to be exercised at a given response time. And it can be, whether it's in minutes or days or hours, whatever the response time is, will be a different program. And they're typically graduated by how much you're going to commit to the resource, how quickly you're going to respond, and therefore how much money you're going to get back in terms of payment. A 2-day response time would certainly not get as much money back as a 1-hour response time, because if the peak hits and the utility must respond in an hour, that's a significant happening, and when it's that critical, the dollars can continue to go up. So the faster you can respond, the more money a person can make. So demand response is typically found in AC systems. Since we're talking about DC, what we do here is really make the meter, the electrical meter, spin slower. So we're taking load away from it, spinning the meter slower, and we never really take 100% of the load or shut the load off of the grid. So in effect, it's again a fairly dynamic response system that fuel cells can provide. One thing I didn't mention is that if you miss a commitment, if you made a commitment, let's say for 100 kilowatts to come offline, and you said I can do that in 4 hours, and you miss it, there are penalties involved typically with utility programs. Peak shaving is another program that, and these are generic terms. Many utilities have their own trade and brand names that they put on these. But the idea is that it's a threshold-based program that says that if I can maintain my power consumption below a certain peak, then I can actually get rebate money or get money back by doing that. So I don't go above a peak load and therefore I don't reach into that area where the cost per kilowatt hour goes up because I'm above a forecasted amount. In a program we looked at in Europe, there was a penalty if you went above a certain forecast, where not only did the energy above the forecast get charged at the higher rate, but all energy for a period got charged at that higher rate. So it was actually retroactive to the base load power that the consumer was using, and therefore it became very expensive. So this idea again is to use the fuel cell asset to prevent reaching a peak point. The next program is very similar, but it's called time of use. And in this case, utilities around the country, particularly those in what I'd say the warmer climates, have got much greater concern in the summertime months when everything's peak consumption. There were, this last year in Texas, as an example, I think there were peak utility rates or utility usage numbers that were hit like consecutive days, month over month in Texas because of the drought that was going on, the heat waves. And so the idea here is a utility would have certain hours of the day where they would say, and maybe it's months of the year and hours of days, where they would be charging a higher rate. And this then is the model where you could use the fuel cell to lower your consumption during those times of use, or those times where the peak rate is going to be charged, and it basically avoids you paying the higher dollar amount. So it's a time-based solution. So in this case, if at 12 noon on every day during the months of July and August, the utility in Phoenix, Arizona says, well, my rate's going to go up from 20 cents a kilowatt hour to 40 cents a kilowatt hour because this is my peak, the fuel cells can be programmed to come on and reduce the consumption for that customer during that period of time, and then shut back off and go on to the next event. Again, preventing that higher cost of energy. So I'm moving now to a hypothetical network and go through examples of each one of these as to what they would mean in a kind of bottom line scenario. So what we've done here is modeled out, in this case, 300 base stations that we just chose in the San Francisco Bay Area, and the considerations were to keep them in a geographical area that would be confined within a utility's operating area. Realizing if you've got a national network, that's very difficult to do. But so you might pick, well, which utility's got the best programs? Where can I do that? And also, where's my grid maybe weaker or have other events? The Gulf Coast being one where, with hurricanes and things like that, people would deploy backup power assets, and then they would have a high enough concentration to look at the utility programs and say, oh, that would make sense to try to qualify or submit my fuel cell assets into a program. In this case, again, we took the San Francisco Bay Area. Access to the sites is important because you have to maintain them. If they're running, no different than any other generator, you need to put fuel at the site. So that's important to have that. The scale of it, so if you've got 20 sites, it may not be worthwhile to do this. If you've got 300 sites, the scale of it becomes important. And if you can commit more resources to the utility program, therefore it's more dollars back when these events happen. I mentioned the fueling, but the important thing here is if it's going to be long-run events, and typically these utility programs are not, multiple days, they're hours at a time, so it's not a huge issue, but you have to keep in mind the ability to then get fuel back to the sites. So again, geographics is important in being able to service those sites. So one of the things that enables this is bulk hydrogen refueling, and it's something that has really been developed over the last 18 months, 2 years. That's new. Traditionally, it's been hydrogen as a fuel like this has been done in welding cylinder type models where you take the steel cylinder out and you exchange a cylinder. A cylinder. In this model, you bring a truck that has a bulk amount of hydrogen onto it, and you connect up to a larger storage facility and refill it on site. And that way, with a single truck, you can service multiple sites, refilling them in position. You're not dragging significant amounts of steel around the roads and so forth. You're just basically moving the molecule to the point of use. So this is a very similar model to propane or diesel in this case, but it has been something that's just been developed and is being used right now in about nearly 500 sites in the U.S. within two or three different carriers that are deploying this in commercial wireless sites, and a photograph there is shown with the truck refilling it. So typical sites, if your person's going to put 200, 300 sites down in a model, this is kind of what they would look like at various locations. These range from, middle of the country, mountainous regions, to deserts, to upper Midwest in these particular sites. The only thing I'll point out on the one side in the very middle of this image is that's a full off-grid site, which wouldn't necessarily be used in a utility program because the primary power in that case is the PV arrays you see in the background, but it is a fairly common type of site that we get involved in. A few more pictures here. Various sites, various sizes and locations, again, mountaintop to desert, to indoors to outdoors, and all things in between. So we'll talk a little bit more about the models and what they mean at this point. So the backup power model, as I said, is really about sustaining the network, keeping the network up and working. So it's really about protecting the revenue. And as a result of that, there's not a financial return in a rebate cash model that you've got in the backup mode. Again, this is all about supporting the customer, keeping the traffic active. It's in many cases today, commercial wireless networks actually carry public safety, radio signals, and so forth, being able to provide a reliable and robust network. The demand response model, and I certainly won't go through every little detailed line here, but I'm sure these slides will be available, and you can kind of look through the numbers if you want to. But basically what this shows is a model that says energy produced by the fuel cell is going to cost about $1.10 a kilowatt hour. Some of you might right away think, gosh, that's really high compared to my 10, 12, 15 cents a kilowatt hour I pay for my grid power, which is true, but the issue is you're not dealing with the normal here. You're dealing with the fringes of the utility. So in this case, when we modeled this, we looked at a utility that had what they call a locational marginal rate of $1.30 a kilowatt hour. So 20 cents a kilowatt hour higher than what the fuel cell would cost to produce the same amount of power or energy. And in that case, it was the utility had to go out and buy extra capacity if they reached that point in time when their grid was getting exhausted right then and there. So it's a spot market price they were paying. In some cases, it can be extremely high when they have to do that, and they have to do arbitrage with other utility suppliers. So in this case, we committed the 5.5 kilowatts across the 300 sites, so it's 1.65 megawatts of power that were actually allowed to be put into this. And again, depending on how quickly you could respond to the request, is how quickly or how much the utility would pay you. So run through the calculation. In the end, there's a lot of money spent, but there's actually also a lot of money returned on this. In the case, there's as much as $150,000 of payback that they get for actually deploying this product set for these 300 sites into this program. And really what they're doing, they consume across all those sites 80 hours of runtime in the year is all. So it's not a lot of time you commit to it, but the value is quite high in the return because it's a critical component for the utility to offer their services. In the peak shaving model, the base scenario is the same. It's the same 300 sites, 5.5 kilowatts per site. But in this case, the end user had their forecast, let's just say at 60 megawatts on an ongoing basis. So they said that's my maximum power forecast. But in their case, they had peak power issues, so they were able to operate the fuel cell and prevent going above that 60 megawatt upper threshold. And in an event, then the utility gives them money back by virtue of cost avoidance. They're not paying for that extra money. So in this case, you're going to run, in this case it ran for 8 events and about $28,000 of return on this. So it's very simple in the model of getting the money back because you're not going to pay that higher rate. Time of use, again, same sort of model, and in this case, the utility in their time of use had a peak utility rate of $1.12 a kilowatt hour, so slightly above what the fuel cell cost to operate, only 2 cents per kilowatt hour. But in this case, they were going to run in those peak times because it's in the hot months of the year, in the middle of the day sort of thing. It's running for as much as 400 hours per year, but you're only saving 2 cents a kilowatt hour. Well, so the bottom line number is not so huge here, only $13,000, but it still is a savings, bottom line savings to the company that had the fuel cells deployed for the backup scenario anyway. So it's just one more way to cover and improve their cost situation. So the summary here, the demand response generated over $150,000. You can see that ran for only 80 hours during the year for the 300 sites. Peak shaving ran a little less, but it was a significantly less amount of return, only $28,000. And then the time of use had run much more, so you're spending a lot of money to get a small amount of money back in OpEx. The CapEx was assumed already done for the backup scenario in all these cases, so you're not trying to repay the CapEx side of it. This is strictly an OpEx model. So in that time of use, you're going to spend, over $700,000 to make a return of $13,000. Not nearly as good as the 150 on the demand response. But nonetheless, it is a return, and it's a positive value back to the company. So the other piece I'll just mention in kind of closing off on the program is that if the assumption is made that backup power is important, and we have these other advantages in the utility programs, we can use a fuel cell as a component in the smart energy programs. Another benefit you get of deployment is comparing the fuel cell operation, and whether it's the 32 hours or 80 hours or hundreds of hours on a case-by-case basis, side-by-side basis. You're preventing the emissions from an internal combustion generator if that's what you're using at the site. In this case, we're showing 300 sites at 150 hours, and it's got significant differences. Basically no emissions on the fuel cell and fairly significant emissions on an internal combustion diesel generator. So there's a significant sustainability factor to this. This is one of the reasons why the state of California has aggressive programs and incentives on fuel cells and similar technologies. So with that, to summarize, energy issues, whether it be here in Spokane, Washington, or in Phoenix, Arizona, as my example was, or somewhere else around the world, they're not going to get any easier for us. Whether it is capacity, demand outstripping capacity, whether it's natural disasters, whether it's other events that cause issues like the outage that happened in Southern California last summer, these things are going to happen. So power and energy issues will continue to be problems and issues that we have to address as an industry. And I think that as we see more and more attention getting paid by utilities and regulatory agencies around efficiency and energy programs, smart grid, being able to manage how we do things both on the supply side and the demand side, these programs are going to become more aggressive to utilize assets that people have already deployed as opposed to buying new assets just for those peak periods. And fuel cells for backup power continue to increase in popularity throughout both domestically here as worldwide, primarily in the telecom space. There's many other applications for fuel cells, but in communication systems, we're deploying in hundreds and thousands as opposed to tens and twenties as it was just a few years ago. So the adoption rate is continuing to increase. Therefore, there are assets available to put in these programs. And the bottom line is being smart with your energy assets is something that's important for everyone to do. The solution is viable with some utilities in some countries or some locations today, and others it may not. So this is something you really have to look at. The application, your utility, your power service provider, and maybe other programs from state and local and federal governments to decide if this is the right thing for your application. With that, I appreciate everyone's attention, and I will come back with Chris on questions at this point.
Okay, thank you, Joe. You had mentioned, you showed a case there where the demand response example, the demand response scenario had the most benefit, the most financial benefit. We have a question from Kenny regarding demand response programs specifically. Is there a database similar to the database of state incentives for renewable energy, something similar to that, that identifies utilities providing demand response programs?
There may be some actually on that database. If you go to the website that's shown on the slide, there may be some available on there. I don't know if there's an aggregated database of all the utility programs. What I would suggest is that you go to the specific utility, to their website, and most of them will have their programs fairly prominently displayed because they like to take advantage of those. They like to promote those ideas. So if you're within a particular utility operating area, I would just go to their website. As an example, we've done quite a bit of work with PG&E, and they have some, it's very visible, and they've got people on call basically to help and assist with, can I qualify, what's my model look like, how does it work for me?
Okay, thanks. The next question is, could you talk about fuel logistics in regards to fuel cells? For example, how readily available is hydrogen, and also what is your experience with bulk refueling?
Okay. The logistics has been, let me just say, improving as the adoption rate of technology and any technology, and fuel cells are relatively new, particularly in the telecom sector. And I said relative, they're 10 years new. Let me kind of put that boundary in it. The logistics have been improving, and really what's come down to is that the last mile services are the most important for people to take notice of. So in many cases, our customers, when it's talking about cylinder hydrogen, will set up a regional depot and then have a third-party services company provide that last mile service. And that seems to work very well. And it's no different than the model they use with diesel or propane deliveries today. And there are literally thousands of outlets around the U.S. for cylinder hydrogen today. When it comes to the bulk refueling model that I showed the picture of, and there was a map that showed kind of delivery radius or circles around where they would deliver. Again, as I mentioned, that's relatively new in the last couple of years, and just today there's again third-party companies starting to say, well, I can get into that business as well. Today, it's the major gas companies like Air Products are providing that service, and the delivery trucks and the fuel. And the experience has been quite good. Again, the telcos, they're the wireless service providers that are deploying products in this space have actually set their contracts up. They have the dispatch methodology figured out, and in the case of recently, there was the storms, or late last year, there were storms that ended up hitting the New England coast, and there were significant outages through New Jersey and New York, and there were several fuel cells in this model that were deployed there, where even though there was the remnants of the hurricane coming through, the fuel provider was able to go out, refuel the sites, and keep them online. There was a lot of press about the sites that were offline. There was very little press on the sites that remained online because they didn't need to be talked about. They just continued to work. But the reality was is that a lot of those sites up there were fueled by fuel cells and this renewable, or excuse me, the refueling hydrogen model.
Okay. Next question: are fuel cell power solutions cost competitive with batteries and generator solutions? I think that's a really good question.
It is a very good question, and it's asked. The business case and the business model is asked everywhere and every turn we go with new customers. And the short answer is yes, they can be competitive, particularly if you look at CapEx, the side of it. I have to qualify with it. It depends, because if I look at a site that's, let's just say it's 500 watts and you want to run it for 2 hours for backup power, I will guarantee you that the battery is probably the better way to go. If you want to run that same site at 500 watts for 2 days without grid power, batteries will become, both from a size and cost standpoint, will become fairly expensive, so the fuel cell would make a lot of sense. So there's a trade-off of, again, how much autonomy someone wants versus what they need to expect to pay at the site. So the comparison several years ago was mainly around batteries. Today it's a little more around generators, and the model here is, as I mentioned in my presentation, the power at sites are typically going down, efficiencies are going up. So the fuel cell is a much better solution as you get lower power. So if you're at 5 kilowatts, 6 kilowatts, 7 kilowatts, and you want to run for 40 hours or 48 hours, it's much better to deploy the fuel cell than a generator that might be oversized for that site, which would mean it might be run relatively inefficient. What we have found with generators at traditional wireless communication sites is that we can compete very favorably on a head-to-head basis when you look at the CapEx model, kind of all in installed cost. We can compete favorably with those. And then if you look at the OpEx side of it for maintenance, fueling charges, and so forth, we look better very quickly. The fuel cell will actually come out advantageous in almost all cases.
Very good. I was reading something about methanol, and methanol, the article I read was methanol challenges hydrogen to be a fuel of the future. And we have a question from Guy. Do you have an opinion on methanol versus hydrogen gas?
Certainly. My opinion is, again, I'll say that the scapegoat answer of it depends. In some scenarios, a methanol solution which would require, there's two models here. There's one that is a direct methanol fuel cell where it takes the methanol, which is an alcohol, liquid alcohol, directly into the membrane and converts that electrochemically in the fuel cell. There's another model where methanol is mixed with water and it's run through a fuel processor to break it down and extract the hydrogen out and then use the hydrogen in a PEM fuel cell. So it depends on the model that in question there, but the traditional one, hydrogen versus methanol, is probably the fuel processor. And again, in some cases, it makes sense to use hydrogen. In some cases, it makes sense to use a methanol solution. And at ReliOn, we're actually, we continue to look at various technology solutions, and we do not have a commercial product today with a methanol solution, but we are in laboratory level work with those solutions in addition to our commercial hydrogen products. So certainly in some cases it makes sense. In other cases, when hydrogen is readily available, the hydrogen probably is the better solution.
Very good. When you drive around and look at cell sites, I know that cell sites are just a small part of your customer base there, but you don't maybe you don't see anything but generators or batteries, or maybe it's hard to tell if there are fuel cells there. So the next question is very good. What kind of market penetration are fuel cells achieving at this point?
Okay, I'll talk domestically here for a moment, and then I'll kind of talk worldwide. So domestically, fuel cells not a solution for every site, and we know that, and certainly the customers that are deploying it know that. And so when you identify sites that have got the right power levels and variety of parameters you might look at, it might be the stability of the grid, it might be the location of it, it might be fuel access. The penetration, if you look across all wireless sites in the U.S. right now, as an example, it's a very small fraction of penetration, honestly. There's certain carriers, certain customers that have actually started to deploy faster than others for a variety of reasons. Some government agencies have looked at it and said, I can start to do this for certain applications. But you're right. I mean, if you go to a site or you drive down the road and you see cell sites, your explanation was interesting, because you'll see a generator, but you'll never see a fuel cell at the site, because it doesn't look like anything other than a piece of equipment that's sitting there. There's nothing that tells anyone differently than a radio cabinet versus a fuel cell, because it doesn't need a big muffler on the top of it. It's not sitting somewhere off to the side. It's just another metallic box sitting there at the site that looks like everything else. In developing parts of the world, that's been a huge issue, because diesel and generators get stolen very frequently. It's not infrequent also in the U.S. When a hurricane came on shore a couple of years ago down in Galveston, one of the transportation companies we dealt with lost 10% of their portable generators due to theft after that hurricane. So the fuel cell is very disguised, if you will, so it doesn't become a target of theft or vandalism. It looks like just like everything else. So we actually like that you can drive down the road and you don't see a big arrow that says, oh, this is something different. We want to blend in. We want to look and feel like the equipment they use at the site every day, and not be disruptive when it comes to that side of it. We want our disruption to be efficiency and environmental issues and reliability. We don't want to be disruptive when it comes to, gosh, that's looking bad at the site, or it's an eyesore or whatever.
Right. Yeah, I think that is smart on your part to think that way. Yeah, I think theft might be on the rise at cell sites. But anyway, looks like we have one more question right now, and that is talking about the incentives. And the question is the U.S. the only region providing the kinds of incentives that would make these kinds of programs worthwhile?
Well, first of all, the answer is kind of twofold. Is that the incentives improve the situation, but don't necessarily are not the deciding factor to make them worthwhile, even domestically here. In many cases, we have customers like in the government that can't take advantage of the incentives, or state and federal, local governments that can't take advantage of that, and it's worthwhile for them already. So those that can take advantage of it, it just is actually that much better for them. And I think that the incentive programs that exist within the U.S. And the foresight that the government had to put those in place, not only for fuel cells but for other alternative energy, was important, because it's driven adoption. It's driven and it's oft overused, but it's certainly driven job creation in some sub-markets and marketplaces. As you look across globally, even if I just jump into Canada and Mexico, there's very little incentives that are similar to what the U.S. has for programs like this. We do quite a bit of work in Southeast Asia, in Europe, and the programs are different that they offer in most of those areas. Most of it is centered around a cost share on a program as opposed to incentive on a unit. So you might be able to go to a government agency and get partial funding for a deployment of 100 sites or something of some magnitude that shows progress in the industry, where here, even if I'm a small regional broadband wireless company that's offering internet services to the Kansas farmers, and I buy 4 systems, I can still go get that incentive and I can apply that to my my cost. That's not very common throughout the world. It's much more you've got to scale, you've got to go really work hard to get that support money, if you will. So we're actually very lucky in the U.S. to have these programs. Up until the end of last year, there was even a more lucrative side of the incentive, and that was actually a grant option that was available, which was had a sunset at the end of 2011. But there's some hope within some of us that might get reinstated as we continue to need to find improved solutions for energy.
Okay, I don't see any more questions coming in, and so we're just about out of time. I'd like to thank you, Joe, and ReliOn for a very informative presentation on smart energy and fuel cells, something that probably most of us don't know a whole lot about, but we do know more today because of you and the very good presentation. And if I want to give you a minute, Joe, if you wanted to say any last words.
I just appreciate the opportunity, and hopefully those that have attended will, scratch their heads a little bit and think of ideas that might make sense to them, or raise additional questions in the future that we can all come together with and get to answers and maybe show some progress in this space.
If anybody has
If
anybody has any questions, there's the contact information on the screen there. www.relion-inc.com, relioninc.com, and Joe's email is there and phone number as well. I'd like to remind the audience that WCAI will be planning another exciting webinar next month. Topic to be determined, but I promise it will be exciting for some of those. So everyone have a great afternoon, and thank you very much.